sir. First share your screen, sir.
Yeah, see if it is visible.
Yes, sir. Your screen is visible.
Okay, okay, sir.
Sir, make it in a full view, full screen view. Yes, sir. Now it is in full view.
Okay.
Sir, let me introduce you before starting your session, before the attendee.
Okay.
Okay, sir. So, good afternoon, everyone. Professor Jatana sir received his engineering education from BITS Pilani in 1983. He worked as IC design engineer at Rockwell Semiconductor Newport Beach, USA, where he was involved in design of 65C series. And after some time, he joined semiconductor laboratory. Not some time, later he joined semiconductor industry. He has hands-on experience in various areas of VLSI like CMOS process development and integration, VLSI design, semiconductor manufacturing, etc. Where he was as a group head, he led a team of 78 scientists who developed more than 75 standard products, all space grade for use in satellites and rockets. These are various types of ADC, DAC, LDOs, communication protocol devices, and etc. Also, he has made few compatible process to baseline, one like PDSY CMOS, LDMOS high voltage, CCT, CIS, radiation hardened technology for space and military application was also developed. Presently, he is now adjunct professor at MNIT Jaipur, DAU Gandhinagar, and also in PGIMER. So here I am welcome you, sir. Please start your session now.
Thank you. Thank you, sir. Thank you, sir. First of all, I would like to express my deep gratitude to you for giving me an opportunity to interact with the participants
Yes, sir. It's our honor, sir. Also.
Yeah, during this faculty development program. And I will be giving you an overview of the complete cycle, manufacturing cycle, like how to make a product, starting from the specifications and what are the issues and what is the scenario. Semiconductor industry worldwide, it's basically a highly segmented industry, and it has very high efficacy to other industries, like chips are used everywhere. So all other industries are based on these chips, which can be a VLSI circuits or can be a MEMS device. Now the total, if you see the industry, it's more than 1,500 billion US dollars. And out of this, $600 billion is the component. By component, I mean the integrated circuits, VLSIs. And 90% of these are 90% of the $600 billion components, they are made using silicon substrate. They are VLSI circuits. Compound semiconductors are also picking up, gallium nitride and silicon carbide, gallium arsenide for high frequency applications. That also is picking up. And MEMS is also around $8 to $10 billion. MEMS sensors, which are micro and nano level sensors, that also is there. So this is the component which is close to $600 billion. Then there is another part which we call it a wafer fab equipments, WFE. So these are the companies which make like Applied Materials, and these are the companies which make wafer fab equipment. So that also is substantial, more than $200 billion industry. Then your EDA tools, design tools, three main players are there, and Cadence, Synopsys, and Siemens Mentor. So that also is close to $15 billion. then testing, packaging, QA, reliability equipment, gases and chemicals, and all those things. So it is close to $1,400–1,500 billion semiconductor industry, catering to various substrates. And most of the substrates used are silicon. Then other things are also, the compound semiconductors are also picking up. 2D materials, lot of talk, but still not at the industry level. There is no product in the market which is based on those kind of thing. Maybe 15–20 years down the line, we can see some of those materials being used in making these chips. But at present, it's only the silicon is the king. We are 90%. Then for HEMT and high power devices, we have the devices which are based on growing epi layers, heterostructures with bandgap engineering, which are mainly used by AlGaN, GaN, gas, gallium arsenide devices. Silicon carbide also, because beyond 2 kilowatt and above kind of power devices, silicon carbide is the best. So those things are also there. Now, in India, it's a big, as you know, it's a big country, 140 crore population. Out of 140 crore population, the market is only around 40–45 crore, you can say, which can afford to buy some of these gadgets, expensive gadgets. But there's a huge requirement as shown in the screens: mobile sets, set-up boxes, your transceivers, modems, and things like that, energy meters, particularly your smart cards. So there is a huge requirement of all these devices. And commercial devices, then we have big railways, we have fourth largest defense. They also need a lot of equipment. And then the atomic energy program, they also need a lot of these kind of devices. And at present, we are not manufacturing any device. We are all chips we are getting imported. There is only one fab, you might be aware, which is SCL, which has been working, and it has a very limited capacity, 1,000 wafer starts per month, WSPM. So now there is a tender which you can see on their website, of Mighty. So they are going to increase, they are going to upgrade this capacity to double, around 2,000 wafer starts per month, and the government is spending close to 4,000–5,000 crore in this for this upgradation. We have some fab equipments which are installed at Sensei, IISc, IIT Bombay, and at many other places. But you cannot make a good transistor out of those things. Some limited experimental academia things can be done there. You can grow some layers, do some etching. But for making a good transistor, you need a very good profile. For that, you need ion implanters. And it's not a one ion implanter. There are 4 different types of implanters, and you need all those 4 different types of implanters for making even a good transistor. So, which can only be made by commercial equipments and not in any academia. So this is the scenario, and as you are aware, we have there is some data available of how much devices India imports and things like that, and in the various areas like wireless communication, $26 billion market, consumer electronics, automotive, electric vehicles are picking up, as you are aware, from scooter, 2-wheeler, 3-wheeler, all 4-wheeler, all sort of things. So lot of electronics, and if you have to make planes, aeroplanes, commercial planes, lot of avionics is there, lot of chips are being used. Then your computers, laptop, and things like that. So all these things are there in the different area, and we need a lot of these micro devices. Now in this graph, if we, as I told you, we don't have any strength in manufacturing, we don't have any facility, a very limited facility, it's not commercial. Like even 2,000 wafer starts per month, compare it with TSMC, which is around 69% of the world's semiconductor manufacturing. They have a 69% share, and their wafer starts per month, they're 14.5 lakhs. Wafer starts per month. That was in the year 2024, which the data is available. So you can compare 14 lakh and 2000, and even this 1000 wafer starts per month also is we are doing quite less than this. Now, if we have to start, as the government has come out with the semiconductor mission plan, where do we start? So in this is my personal view. In this smartphones, we cannot make a chip for which can be used in smartphones. It's very, very tough. You cannot compete Intel. You cannot compete other Qualcomm, Broadcom, who have around 40, 50 years of experience in this area. And personal computing. So these servers, it's very difficult to produce a chip here. And not only there is a design angle, there is a manufacturing angle too. Because whatever you are doing, one thing is design should be good, then your reliability of that product. All these chips, they should be reliable, they should work for 20 years. You have to ensure that. So the best area in the present scenario when we are starting is the industrial and automotive, where we don't need very, very small size, small channel length transistors, because these are all mostly high-end analog. Even in the mixed signal, 70-80% is analog and 20-30% is the digital, which is mainly generation of various clocks and interrupt signals and things like that, and some memory. So we have to start with the products which falls in this area: industrial electronics, consumer electronics, and automotive. Wired and wireless also is very tricky. It's not that easy to do. Why do we want chips made in India? So these are the reasons. I think you will all agree. And on this, I need not elaborate much on this. And why there wasn't a fab in the last 20 years? There are many reasons. And the main reason is like capital. It's a very high value. The capex required is very high. That is close to, even if you have to set up a modest fab. Modest fab means say 90 nanometer geometries and 40K wafer starts per month. If we have to set up a fab, this kind of a fab with all new equipments, it will cost you close to $4 to $6 billion. So that is a huge money, and the break even will come after 9 or 10 years. You see, this is the total cost, and around 8 to 10% of this is the recurring expenses. This is the capex. So every year you have also to sustain those operations. So you have to spend a lot of money on this, and there is an uncertainty. Whatever product you are making, whether it sell, whether you will be able to get the desired yield. Intel struggled below 10 nanometer on their yield. Their yields were less than 10, around 10-20%. So if you are getting this kind of yield, you will end up losing money. So huge capex requirement. Operating expenses are very high. All the gases, all the materials, machines, chemicals, gases, whatever accessories, spare parts, consumables, they are not made in India. You have to import it, and you need very good power, lot of water. You need lot of water and very good power, clean power. So in the later slides, I will tell you what do we mean by clean power. There should not be any ripple on the 50 hertz. On the 50 hertz, 440 volt line, there shouldn't be any ripple. There's a very high requirement of that. So all these things, and besides this, we know we don't have the good trained manpower in running these facilities, in the process side also, and in running these kind of facilities. So that is the reason, and we don't have this. And nowadays, since that COVID era, there was disruption in supply of semiconductor devices. So all countries have started focus on this particular area. particularly because of the geopolitics, which you are aware, between China and Taiwan. Taiwan accounts for around more than 70% of the semiconductor manufacturing. So US is and whatever chips US is using, they are being manufactured in Taiwan. And so United States now has given a lot of impetus to manufacturing within the US. Around more than 5-6 fabs are coming. 2 Intel fab, 2 TSMC fab. They are coming in United States, and they have a CHIPS Act. The government has, I think, given $52 billion in subsidies, like European Act and South Korean Acts. India government has given $10 billion, and a lot of schemes have been proposed under Indian Semiconductor Mission. And some of these schemes, they come under 76,000 crore, which is $10 billion. Government will give 50% of the cost capex for semiconductor fabs, display fabs, and packaging, testing and packaging things, and then compound semiconductor fabs, and which can, or the photonics and sensors fab. So under these different categories, 50% support. Then there is a PLI, production linked, and DLI schemes are also there, and C2S, which is mainly for academia. More than 125 academic institutions are part, where MIT is giving them funds to design some product, free EDA tools, free fabrication, testing, packaging. Besides manpower, 2 to 3 technical staff is being given. So these are the projects which have been cleared, and you will be aware the only one fab, Tata fab, which is under technology transfer from PSMC. PSMC is not amongst the top 7 or 8 companies in this area, in this field, but the topmost, they refused to set up any facility in India, so we had no option. So Tata has gone for PSMC. They have not told with which technology they will start. Probably it will be 130 or 110, but those things they have not so far told clearly. And they will do the their fab will be in Dholera, and testing and packaging facility will be in Jagi Road, Assam. Micron is only an ATMP, testing and packaging. All other units are only ATMPs, and some are offsets also. So these are the units, and which have been cleared. This is C2S Pro. I will not go in much detail. So these are the terms which you are already aware. I will not spend much time. Now it is very essential to know about various verticals. You see, we have here the main, as I told you, it's a highly segmented industry. Like, for example, compare healthcare. You go to any hospital, there is a eye doctor, ENT, skin, bone, ortho, and cardiology, neurology. So there are around 20-30 different disciplines. So each discipline is highly specialized. So there's a lot of depth inside that. The same thing is true for a semiconductor industry also. And here, the very basic, the very, you can say, the heart of the semiconductor industry basically is the process technology. So what do we mean? What do the process engineers do? They will design components. They work only at components, and components can be active, components can be passive. Okay, active components, for example, if we say there will be transistors. Transistors, broadly speaking, there are of many types. BJT is there, MOSFETs are there. MOSFETs are also different types: NMOS, PMOS, there's an LDMOS, there's a VMOS. These are high voltage transistors. Then within NMOS, the voltage, like we have 1.8 volt device, we have 3 volt device, we have 5 volt device, like this. Now within 1.8 volt device also, we will have a device which is having a normal threshold voltage, which we call it VT normal, high VT, VTH, low VT, VTL. So there are 3. So there are, and then there are the devices which we call it native transistors within 1.8 volt itself. So there is a wide range of devices available, and the design of each device is different. So the process guys, they will design these devices, and by design means all the you can say geometry, lateral and vertical geometry. I will show you some of the pictures. So they have to design those. Is design part is one part, then finally the design is a paper design. How the device will be made actually. So what are the different steps? What are the processes involved in that? So complete steps, complete unit processes. Then in the process, they also have to design. They also have to design the process. Like if you have to grow an oxidation, if you have to grow a oxide layer of 5 nanometer, so the unit process will be what kind of gases you will need, what will be the flow rate, what should be the temperature, what should be the pressure, and how the gases will be inlet, how they will go the outlet, because all these are a chemical reaction. And the compatibility of the two films, the thermodynamics of that, can that two films sustain a particular temperature, what kind of stresses and strains will be developed in these two films, whether these two films are compatible or not, chemically, mechanically, electrically. So all those things they have to see. So it's a, you can say, very comprehensive job, and that is the reason the process technologists, process engineers are highly paid in this industry. And one can learn process only in a while working in a fab only. And as we don't have any high volume manufacturing fab in India, only SCL is fab, uh, which is, you can say, more or less with a very modest manufacturing levels. So that is why we don't have much expertise in this area and how to make these processes. So we are dependent on technology transfer only. And that also, if we are able to absorb whatever technology we are taking, that also is a big thing. So this is the process part. Then we have the design technology, where VLSI design, where India, as per some reports, we have of the world's total design, India contributes 20% or 25% kind of thing. There are thousands of engineers working in different MNCs in Bangalore, Hyderabad. But the only issue is we don't have any IP. Those particular engineers, they are working on a small module. Like most of them, 50% of those designers, they are working on verification job in a digital domain. They are doing verification of a module level, not the complete design, because as you know, it's a bottoms up approach, and there are several modules, and each module has to be verified, layouted separately, and then integrated to make a complete chip. So they are working at a module level, and they don't know where it will be used and how it will be used, and only the verification part. And some will be doing the physical verification, some may be the front end verification kind of thing. So we don't have an IP. There are few companies, 2-3 startups which have grown big, which are developing their own product. And MIT has given impotence, lot of importance to development of Indian design houses, and MIT is supporting. If somebody has a good idea, good product in mind, so we should be able to develop our own design IP. And then there is a manufacturing technology. Now, you see, these three things are related. One is the process, people who will design the process. Designers, they will do the circuit design. Fab people, they will, now the circuit design people, they will release the design in terms of a GDS tape, which has information about all the layers. That will go to the mask engineer. The mask people, they have to make masks, and the GDS will be changed. There are some optical corrections, OPCs. There are resolution enhancement techniques based on the litho. So they will change those GDS and data, and they will make the mask. That mask set will go to the fab, and fab will use those mask sets and all the information which is given by the process in terms of the batch flow, unit processes, and things like that to the fab. They will run those batches, and it is the responsibility of the fab people to ensure yield. Yield has to be stabilized. Yield has to be, first of all, close to some more than 90%. and they have to be stabilized from batch to batch. Okay, so there is and now the designer, while doing the circuit design, he need not know entire thing about the transistor. So he should know whatever is relevant to him, and that information is given in PDK, process design kit, where the unit processes are not given. Only the design related information is given, which we will see in the next few slides. So this is how the link between these three is in terms of the PDK. So the fab people, they will mask fab is also included in the manufacturing technology, and a lot of things goes in the mask fab, because you see 248 nanometer and 193 nanometer laser litho is used to print structures which are 20 nanometer apart, and as per Rayleigh rule, Rayleigh law, the 148 192 nanometer can only print two lines with a resolution of the same 190 nanometer only, but we are able to print even 20 nanometer. So that is due to various techniques, and those techniques are related to multi-masking and even the resolution enhancement techniques, RET, and optical proximity corrections and things like that. So making a mask also is a you can say one of the challenge, and it's a interesting thing, and it's a part of the manufacturing technology. And then the fab running those batches. Then there is a fab. There are more than 200 different types of gases, chemicals are used. Some of these gases are bulk. Bulk means it's not feasible to have gas cylinders. You need in huge quantity. So you should have the gas plant there itself at the site, like hydrogen, nitrogen, and these argon, these kind of gases, they are needed in huge quantities. So you should have a gas plant there itself, and managing 24 hours of these various utilities. You need vacuum, you need compressed air, and there are a lot of then water, clean, ultra clean water. So all these things, huge amount of utilities are required to run that fab. Then quality assurance and failure analysis is also a very big thing, because only thing is you have to stabilize yield, you have to ensure you get proper yield. If there is some batches, some yield is not coming, there are failures, you have to analyze. There are various tools which are used in failure analysis, because nowadays, as you are aware, even at 180 nanometer, we have 6 metal layers. Transistor is sitting, you can say, on top of the transistor, there are 6 metal and 6 dielectric layers are coming. So to diagnose, to do a failure analysis, what went wrong, is also needs very good experience, and it's a challenging thing, and it requires some tools which are quite expensive. And then you should be able to tell about the life of the product which you are making. So quality assurance, reliability, so all these is another big thing in this. And then finally, after the wafer come, the wafer has to be tested, and you need automatic test equipment. Test program has to be developed. Then it has to be packaged in a device. Then the device also has to be tested. So all those things, you need good manpower which are trained in each area. Process engineers, systems engineer, VLSI design engineers. Again, there are many categories in VLSI design. RF designers are different, digital designers are different, memory designers are there, standard cell library designers, analog designers. In analog, some people will specialize in only ADC, and within ADC also some people will specialize only in sigma delta. So it's a highly specialized area, and you have to go in quite depth if you have to make a good product. That is the point I want to make. And then there's a lot of waste, very dangerous waste. You have to manage those waste. This I will there are 2-3 slides on each of these aspects which I will show you. This is the complete flow which all of you are already aware. So the layout, only point I want to make it, after layout, design goes, there's a, for a digital design, there are a number of steps. It has to be done step by step. And after layout, as I told, it goes for the mask generations. So the mask engineers, they will do all these DRC OPCs. And finally, the mask sets will be generated and it will go to the fab and they will do, then the wafer will come and then the testing and packaging and things like that. And the PDK, as I told you, it has a lot of information, and PDK is the bridge between these three verticals. And foundries generally make, the foundries who manufacture silicon wafers, they will make PDKs, because otherwise without PDK, a designer will not be able to make the design. Then your EDA vendors like your Cadence and Opsus, they also build PDKs, because you have to use, for a design, number of transistors are more, so you have to use tool, and if you have to use software tools, the EDA vendor should be aware of the PDKs. So that is the reason they will do. Then fabless companies like your TSMC, Global Foundries, they design they will make their PDKs, and the fabless design houses, they will use PDKs, and IDMs also use PDKs, ASIC vendors use PDKs, system designers. So these are the people who use PDKs, and these are the various components of a process design kit. It will contain the list of whatever components are available, legal components, the name of that component, the component number, the specification of that component, and the design, how that component can be used in the design, the schematic capture, how the component is layouted, how you can simulate that component, and what are the various layers of these components, how you can verify the physical design of that component. So all these information, it will be contained, and including the parameters, the IV characteristics at room temperature, how those characteristics vary at high temperature 125 degree, low temperature -55 degree, how the parameters they vary. Then the parasitic information, parasitics RLC of those components, and then the mismatch. Mismatch means if you are placing two components nearby, what kind of mismatches will be there in VTs and things. So that also the PDK will tell you. And then these parasitics and the temperature effect on these parasitics at high temperature, low temperature, various temperatures, how it will affect. So all that information is contained in the PDK. So that will guide you how to use the PDK. Now, a lot of process options, if you see, are aware. So how the designer choose a particular process, that based on his requirement in terms of electrical parameters, what kind of bandwidth, what kind of speed, what kind of voltages, how much logical gates will be there in his design, how much memory will be there, whether it's a pure digital or a pure analog or a mixed, which component is high, analog or a RF or a digital or a memory. So keeping in view all those things, and what kind of chip sizes he expect, because finally any product has to be sold in a market, and the price will decide that. So based on that, he has to choose between various process nodes. And these are some of the process nodes which have been given. If you have to design some AI, nowadays a lot of talk about AI, ML, machine learning, deep learning, and accelerators for AI, ML kind of thing. So there you need very high speed processing. And if you have to use very high speed processing and you have to make GPUs and AI accelerators, which needs a lot of, like you can say, various cores of the processor. So naturally you will use a very low geometry, very low channel transistors, which are below 10 nanometer kind of thing, which are FinFETs or gate all around and back metal and FinFET kind of thing. So all these three They are basically for high-end processors. And but if you are making a mixed signal or a analog product, then you can go for a you can say soy silicon on insulator, which is a PD, partially depleted soy and fully depleted soy, those kind of things. And high-K dielectric technologies are available for high speed. So there are different technologies available. And for image sensing, there's a CMOS image sensor where you can do back and front side illumination. Both side illumination is possible, which are used in HDR cameras. And then there are some companies which are giving BCD, bipolar CMOS digital. So that's a very, and it's a power, you can do some very high end voltage regulator. So this it power management devices also you can do, and you can put a lot of memory in that. So these kind of things are available. Then there is a MEMS technology, which are basically sensors. All types of sensors can be made on silicon and with some electronics. And then photonics, various types of, as you can say, you can make photodiodes, lasers, and things like that, transformers, waveguides, etc. Okay, so this how to build PDK flow and all those things I will skip. And again, this one of the main component of PDK is the technology file. And the technology file will give this information of the various layers. It will have a layer name, layer number, layer abbreviation, and color of that layer. Color is not shown here. It will have a color. So that you can use it, you can see this. And PDK can enable can integrate a design flow very, you can say, easily. This is an example of a band gap reference. So you have made a schematic by using a schematic capture of Virtuoso. You can say schematic editor. Virtuoso schematic editor, use schematic capture. So these are the various components. You can pick these components and draw the circuit like this, and finally simulate this circuit. And if your functionality is met, next thing is you go for the layouting and call P cell of each component, which is a parameterized cell which has P cell which will have all the information about the various layers used in this device as shown here. So that when you call the P cell, and finally they will do the layout like this. And the only thing is you will have interconnects, you have to connect manually yourself, so that the paths, all the nets, total length of the net is minimized. And then you can use by a SPICE simulator to simulate the circuit, as basically it's a band gap reference. So you can see how the voltage changes with respect to temperature. So this is the temperature from minus 55 to 125 degrees centigrade, and how the voltages change with respect to this much temperature range, so that you can verify. So this is how the PDK enables all these things, to lay out this component by using P cells, and then by using PEX, parasitic extraction of the information, the parasitic information of the nets and of the transistors available. So that also is there, and based on the parasitic information of the component and the nets, the circuit will be simulated, and you can plot with respect to two variables and see whether the functionality which you had meant, whether it's meeting or not. So this is what it means. And parameterized cell, it's a very convenient way of making of layouting. And you can see for even your inductors, now if the file is there, fixed file is there, or fixed value of inductor, and a P cell, you call that P cell of that inductor, it will give you a layout like this and this. You don't have to do the layouting for an inductor yourself, but the P cell will give you all the information. And then these design rules are there, which you have to see, which are width rules, and there are a lot of design rules. Like in our 180 node, there are more than 300 design rules. And there are different types of rules. There are spacing rule, width rule, enclosures, antenna, high voltage rules, latch up rules. And there is some poly and metal fill in the design, though the tool will fill automatically where the empty space is there in the design. So there some dummy fills have to be done. So all those things I will explain you with the one design layout rather than going here. And then each VLSI product has to be, you have to test with respect to the electrical ESD discharges. And these are the human body model or charge device model or machine model. So there are different models available. And based on these models, your device should be able to have that kind of strength, built-in strength for electrostatic discharges. So there, so that the device is tested at the end at each pin, so that it is able to sustain around 1.5 k voltages. Sorry, around 1500 volt DC voltage if by electrostatic discharge is there on the pin. So the device should be able to sustain that. So these normally in the pads, there are ESD protection diodes, which the fabs will give you the IO pads, and the fabs, they normally build the IO pad, and they are the IO pads are built keeping in mind ESD production circuitry in nature. So I will show you some of these things, and antenna effect and things like that, latch up protection and all those things. There you have to ensure that. Now I will skip some of these, and I will rather go to the to show you some of these design flow also. I will skip. This is so now this each for the benefit of the analog designer. As I told you, there are a number of various different types of transistors. For a digital design is mainly based on standard cells. There are different type of standard cells also, like high voltage cells, your low power cells. So the tool, depending on your requirement, the tool has to select after synthesis the cells from those standard cell libraries which will meet those specifications of a speed or a power. For an analog designer, a lot of RLCs are used, passive components are used, and the designer has to make like if the circuit may have requirement of a 50 ohm resistor or a 5k ohm resistor and 5 mega ohm resistor. You cannot use the same film for all these things. So there are a variety of different variety of films are used for realizing those resistors. So there are different types of resistors. Resistors can be made in well can be N and P. So the sheet resistivity will vary. Resistors are also made in diffusion. Diffusion can be N and P. Again, their resistivity will vary. Resistor can also be made in poly, and poly can also be implanted with N plus or P plus to different dosages, so that sheet resistivity can vary. You can have a medium poly or you can have a high poly resistors. Then there are resistors in metal level which are very low sheet resistivity, very low resistance in milliohm per square kind of thing. Then you can have salicylated resistor, non-salicylated resistor. You can have a 2-terminal resistors, and you can have a 3-terminal resistor. 3-terminal resistor means this resistor is sitting in a well, and there is a well contact also, which is another terminal. So this resistor is isolated from the substrate, so it will not let any interference or crosstalk kind of thing. So 3T resistors are very popular and for realizing many of these analog circuits. So these are the names given for the different type of resistors, their spice name, and their sheet resistivities are not given. So each type of resistor has 3-4 positive points, 3-4 negative points. So it depends on the designer which one he chooses. based on his requirement. Then then there are capacitors available, and capacitors nowadays they are basically MIM caps, which is having a density cap of 2 femtofarad per micrometer square. So you can use MOSFET also, where the density is high, which is 10 femtofarad per micrometer square, but you can use in a limited range, that you can use only in the accumulation range. So it's a accumulation capacitor, but the density is quite high as compared to an MIM, metal insulator metal. Then you can have two stacked MIM capacitors where this thing will become double. And then many of these foundries, they will give you BJT devices also, PNP and PNP and NPN. They comes in two varieties, lateral and vertical. They are of fixed sizes, as you can see here in Tower Jazz. They are giving these vertical PNP. These are the sizes: 10 micron, 5 micron, and 2 micron. And vertical PNP, 1.8 volt and 3.3 volt vertical PNP of these. And these are the spice name, and these are the voltage ranges. So these devices, they are available, and you can use these. Where BJT device is used, you see, in a circuit where you need to pump in lot of current. Maybe you are driving some actuator which needs more current, say around 100 milliampere or more than this is needed. So you may use a BJT device to pump in that kind of a current. Choosing a metal width, how you choose a metal width? So each, normally in a process where you have say 6 to 8 metals, the first 6 metals, their metal thickness will be close to 6500 to 8500 angstroms. The top two metals will be very thick, maybe 20,000 or 30,000 angstrom thick. So their current carrying capacity will be more, and their resistance will also be quite less. So, and when you are realizing an inductor, you will realize the inductor on based on the top thick metals, because the sheet resistance is less. So you can have a very good uh, inductor, and nowadays it is possible to realize inductor till 10 to 12 nanohenries kind of values. It's possible to realize in a chip. And these are the broader specification, what kind of width will be there, and what kind of, this is the minimum width of a metal line, and the spacing between two. There will be, if two lines are going, so there is a specification between the minimum width and this spacing between two lines from the process point of view, from the litho point of view. So these are those any specifications. Just a sample of spec of a 1.8 volt NMOS and PMOS. As you can see, the NMOS ID sat will be 600 microampere per micrometer, and IOF is only 15 picoamp per micrometer. So you get 600 micro 10 power minus 6 by 15 pico 10 power minus 12. So you can see you get this kind of ion by IOF, which is a very good. And VT is threshold voltage is close to 420 millivolt threshold voltage. This is nominal threshold voltage. So some high threshold voltage transistor will have 100 millivolt VT, which will be higher than this. So inverter gate delay is of the order of picoseconds. Transistor speeds will be around 65 gigahertz FT of a 180 nanometer device. Of a 130 nanometer device, this is around 80 gigahertz FT of single transistor. So all these specifications, they will vary, and this PDK will give all this information, and voltage and temperature range of each they will give, because various types of parasitic resistors, they will have some range. The diodes, they will have some voltage range. So all that information is given in this. So these are some of the sample designs which we did. This is an onboard controller which is used in the satellite. It's basically a controller which controls the operations of the satellite, and it's a radiation hardened, and it is actually used in the satellites. And there's an LDO. There's an LDO because from the outside we are getting 3.3 volt supply, and this is a digital circuit. It works on 1.8 volt, and 1.8 volt is being generated inside. So there are huge number of gates in this standard cell gates. That is why you are seeing this kind of coloring in this. We are unable to, and this dimension is close to some 10 mm, 1 centimeter by 1 centimeter device. This is a Ajit processor, 60 bit processor, which was designed by IIT Bombay, and we did the backend part of this. Professor Madhav Desai of IIT Bombay, he had done the front end, he had given the code, and we did the synthesis and all layout. These are the memory cuts, and this again dimension is 11.5 mm by 11.5 mm. These are the various cuts. There are more than 100 different memory cuts, and while doing the floor planning, you have to see how these memory cuts should be placed. Placement of these memory cuts in the floor plan will decide the actual performance of the circuit, because these memory cuts. Why this memory is placed here? Because this memory might be the logic here, which is in the neighborhood, is addressing these memories, and the logic here is addressing this memory, so that to improve the functionality, so you have put these memory cuts close to the logic, which needs that kind of a scratch memory, and it's a SRAM which is being used as a scratch memory. This is a baseband processor for NAVIC. This one is one pad. This one is one pad, and this is the 12.5 millimeter. And all these things, they have more than 1 million gates. They have more than 1 million gates in a chip area of around 100 to 120 mm square. This is a low dropout LDO. As you can see, it's analog. Number of transistors are less, and that is why you are able to see the various lines. So this is the IO pads. This is the IO pads. Here you can see this black. This silicon is not used. So there it will be dummy. You will do the dummy fill here. Some dummy structures will be put, and the tool will do it. And there's the rule how to put those dummy layers. And you can see this line going. This is on the top metal. This color is on the top metal, and it's a thick line. And this also is the top metal. One of the top metal 4 and metal 5. They are VDD and VSS kind of things. And this one, this line, this is you can say it's a power rail. So it will go like this, it will go like this. And there it will be connected to the power pads. And similarly VSS and things like that. So here the black area, here a lot of dummy fills will be there. Here a lot of dummy fills will be there, which is not shown. So that then the image at least looks clear where the components are there. If we put the dummy fill, nothing will come out clearly. So this is one LDO, and we made a multi-channel LDOs. You can see we have put that circuit is getting repeated. So you can see here this is getting repeated. 1, 2, 3, 4, 5, 6, 7, 8. So 8 of these circuits are getting repeated. So it's a 8-channel. This is a RDAS, which is a data acquisition system. It's a ADC, 16-bit pipeline ADC. So these are capacitor banks. This is the digital circuit timing, and all that is being generated here. So these are the various stages. These are because nowadays it's a switched cap. So a lot of capacitors are used, and capacitor bank has to be layouted in that particular manner. This is a voltage reference, and here you can see clearly the pads. So you can see the pads. So these are the fills to connect two pads. This is the dummy structures. This is the dummy here. This is there because the chip will be diced, and dicer will go like this and will go like this. So at the corner there will be lot of stresses, and that stresses should not spoil your circuit. So that is why there is a metal, extra metal structures which are put, and these metal structures will take that stress, and your circuit will be protected of that. And so you can clearly see the metal lines here. And this is ADC. So you can see the different stages of the ADC in this. This is again one ADC which is a 24-bit. It's a sigma delta radiation hardened. This is used in actual rocket in launch vehicle. This is the decoupling cap. This is the distal part, and this also works on two supplies from the outside. We get only 3.3. This circuit is LDO. It makes 1.8 volt, and 1.8 volt is supplied to this particular distal circuit internally. And this same circuit, this is 3.7 by 3.7 mm. So we made a 16 channel. So you can see the 16 of those are being put here to make a 16 channel, and area is 8.5 to 8.5. So this circuit is being used in space, and SC1203, and it's a radiation hardened. It has no effect on the radiation. So this is, so now if we see below 350 nanometer, reticle is made, because it's not a entire wafer is not printed, only a small area which is normally of the size of 26 and 26 to 28 mm, and in lower nodes it is again close to 28 to 30 mm kind of thing. So that forms one reticle. So this is one reticle. So this area is, say, you can say 26 by 28 mm. Now you can put either one design in this, or you can put as many design as you like. So this is one design. So as you can see here, this design may be 7 by 7. This is another design, maybe 10 by 10, like this. So you have to, this much space is available, so you can put a lot of designs here. So these are the design numbers which are given. So that is known as multiple product wafer, which these foundries do. In one reticle, they will put many designs, and reticle size is big. Depending on the size of each chip, they are able to accommodate each, and you have to keep some space here, which you are seeing, because finally it has to be cut. Finally, it has to be cut, and this area has to be kept. So this area is scribe line, which we call it a scribe line. And scribe line, normally, how much you have to keep? Normally, it's 100 micron. And this is a scribe line, and here we will put lot of monitors, which will known as SLM, so scribe line monitors. So these are the test structures which are put. These test structures will tell the health of the batch which has been processed, that those components, whether they are coming in the specification in the specified window or not, so that it will tell. So these are some of the things. Now I will spend some time on a particular process. What are the issues in a particular? Some of these things I will skip, and I will go to the process. Now in a process, these are the you can say different kind of challenges in a particular process node. We talk about process flavors, like we have a 90 nanometer process. So what are the different process flavor? So what do we mean by process flavor? Means, what sort of BJT devices I am having, then whether I am having high voltage devices along the CMOS devices, whether I am having imaging devices also, whether I am having RF models and RF components in this. So these are the various process flavors, whether a triple well is there for isolation or not. So all these things the process people have to consider. What type of wafer they when you design the process engineer has to keep in mind, like what is the starting material, whether it's a P substrate or it's a N substrate. Then what is the resistivity? What is the doping level of these substrates? Whether it's a, there are various types of wafer, whether there's an epi wafer, where epi may be n plus on n plus plus, n plus on p plus plus. So there are huge varieties of wafers available, and there is a soy wafer also. So what sort of wafer? And there are test wafer, there are process wafer. To give you an idea of the cost, test wafer like 8-inch wafer, test wafer may cost $30. Process wafer may cost $200. Piece of wafer which is 70% of the time used. Epi wafer may cost as high as $600 per wafer of an 8-inch. So depending on the process flow and all these things are there. Then then there is a equipment. What kind of equipment? Because the process also it depends on the fab equipment, like your thin film, your ion implanter, your lithography, whether you are having a stepper or a scanner, ion implanter, whether you need all those high voltage ion implanter, high current ion implanter, low current implanter. So you need different types of, if you have to do angular implant, you need a different type of implanters, etcher, dry etchers, wet etchers. So all these things you need. And then finally the process people, they have to worry about the fab people, they have to worry about the uptime of these equipments, the stability of the process, how stable the process is. Today you are running a process giving 90% yield, but after 6 months, after 1 year also it should give the same. Normally the machines drift, so you have to see how they are drifting and what you have to do to see they are not getting drifted. And when you set up a fab, initially when you are setting up a fab, you have to run certain batches, because finally the spice models, they are dependent on the fab. So you have to generate a lot of test structures and you have to extract different parameters, and those parameters you have to model it, and you have to make models, and then you have to make PDK based on you have to freeze your design rules, your DRC, LVS, and all those things. You have to do that when you do set up a green new fab. And maintaining a clean room class 1 has to be maintained in case of a fab. There are various gases and chemicals. I will give you some information on that. And then so in a process, like if we tell about 180, if the number of steps is close to 540 process steps,
उसको बोलिए कि उनको 205 नंबर रूम न्यू एकेडमी कॉम्प्लेक्स में बैठे हैं.
540 different process steps are there, out of which close to maybe 150 they are cleaning steps. The remaining are the process steps, and each step they have to be when you design a complete process, so you have to design first unit processes. And to give you an example, we have close to 130 unit processes. So you have to make perfection of only one thing, which I will explain here. And in that there are 130 unit processes, and after that all these unit processes have to run one after the other in an integrated manner. And but the second process should not affect the first process which you have already done. So that process has to be designed in such a manner. So what is a unit process? Like, you see, this is the starting material of a wafer. Most of these wafer are grown on CJET process, Joe-Chelsky process. So it has to be pure silicon, 100 crystalline structure. There has to be certain impurities, though we want 100% pure, which is not possible, but there will be some carbon, there will be some oxygen, there will be some hydrogen. the densities will be close to 10 to the power 8 per centimeter cube kind of thing, as you are seeing here. So these are those impurities in this. But what we want is like our wafer, 8-inch wafer is around 725 micron thick. We need only the top layer, few microns, 10 micron, 5, 10 microns, where we are interested. We are not interested in this bulk. Why this bulk? Because 8-inch diameter is there. It has to go, it has to see 1200 degrees centigrade temperatures. And besides, you have to hold the wafer by vacuum. So it should have some mechanical strength. A 8-inch diameter disc, if it is 5 micron, 10 micron thick, it will not be able to take 1200 degrees centigrade. There will be bow and it will break. It will break. So that is the reason why 725 micron thick is there. But there is a first step is a annealing step. You can see this. After annealing, what I have done is I have pushed these impurities which are at the top to the down. There are various annealing techniques. These are known as gathering, which you might have studied, backside, front side gathering. So I have made this area purely clean. There is no impurity. It is a very small area, 4 to 5 micron kind of thing, and all other impurities have been shifted. I will do the processing in this area, and after the wafer is tested, the wafer is lapped. Lapping is a packaging process where the wafer is cut. Like I will cut the wafer from here, and I will use only this much area. And there are on the top also it will add some 4 5 around 5 6 micron. It will add depending on the number of metals, and 5 6 micron there. So total will be around 15 20 micron thick chip will be there, which will be packaged in a very thin. Nowadays, the TSOP packages, they are very thin outline packages. So that is the how it is done. And the first step in the process, which are below 100 nanometer, is basically the definition. You have to define the areas, active area and your field areas. What a field area means isolation. You have to define the isolation. And active area where the transistors are made, and where the transistors are not made, that will be the field area, which is isolation area. Earlier for isolation we were using LOCOS, which is a local oxidation, and but there are issues in that local oxidation. But below 180 we are not using LOCOS, we are using STI, which is a shallow trench isolation. STI, shallow trench isolation, is being used. So you have to build trenches and shallow trenches. This is one example. So this is a trench. These are the real pictures which of our SCL fab taken on as these are cross section images. To, as you know, there are skilled people who work on these TEM and SEM, because these are cross section images and you have to cut the wafer at a particular angle. So you have to prepare sample, then only you can take an image. And where that well is, he should have some idea, and normally they will cut at 5 6 places, and maybe one of the place will give the correct geometry. So this is the thing, and I have to make a trench like this, and then I will have to fill it. And you can see here, this is the trench which has to be made. This is the trench which has to be made, and it has to be filled. And because finally this is the first step. And what it involves etching. You have to etch this area first of all. First of all, there is a mask for that. Mask will have this geometry. Based on this geometry, and you will have to etch this area. You have to etch the silicon. And there is an aspect ratio. So etching is aspect ratio is 1:3 or 1:4. So you have to do an etching at a particular angle. And etching is at this is not at a 90 degree. This is at a particular angle which is 74. So this angle is not 90 degrees. So you have to do, and this is the your trench. So this angle, it has to be at a particular angle, and there is a reason for that, because at this wall we don't want any you can say leakages current. If it is at a 90-degree, there will be leakages, and then that principles of quantum physics and all those things gets involved. So that is why there is the etching has to be at a particular angle. And now the process engineer has to decide what should be the depth of this, what should be the width of this. And finally, this is the first step. After the step is done, before the wafer will go to the next step, but the next step machine which should know where that wall is. So there has to be some identification mark. And how? So for identification mark, we have to make this divot, this kind of structure, this divot. This is a divot. So this kind of, here you can see, this is a divot. So you have to make this kind of structure will be there. And you can see here, a divot will be there. So the second machine will take this as an identification mark, and they will know between two divot, there is a trench. So, and between two divot here, within this geometry, there will be a trench. So finally, he has to decide based on now what the goal is. Our goal is to pack maximum components in a given area. So my packing density has to be maximum. For a packing density, if it has to be maximum, then I want to maximize active area and minimize field area. So I should be able to make a trench which is as small as possible. Okay, so that I don't, because that is an area which is not being used. It's only for isolation, like in a house, in a boundary wall. Whatever, if you make more thick, it won't serve any purpose. Rather, it will be wastage of space. But you cannot make it very thin also, so that in just with a small wind it breaks. So that also is not possible. You have to arrive at a particular dimension. Okay, so these are the things. An STI, you have to make a. So now the unit process, what I was saying, in the process engineer, the first process will be the etching of a particular, this kind of a, he has to etch that area, create this trench of a particular dimension with a divot like this. With this divot will be created afterwards when we deposit the you can say high dense dielectric on that. That time it will be created. The objective of the first you can say the person who is doing this process step, which is a unit process, is only to do the etching of a particular, to etch this particular thing of a particular dimension at a particular angle. And it's not a 90-degree angle, it's a angle at some this thing. And he has to ensure that at the corners, so corners will be two. At the top there will be corners, and at the bottom here also there should not be any stresses at the corner. There should not be any stresses at the corner. So taper angle stress versus leakage trade-off is there. So he has to do that. And finally you can see this is how it comes out. So how do we do first? First you start with the wafer, and the wafer, it has to be, you grow an oxide layer which is around 145 angstrom, and on top of it you grow a nitride layer which is close to 1188 angstrom. You grow a nitride layer, and then you define this particular, you define this pattern where it will be etched, and finally you have through a mask. And once you have defined that, so as you can see here, this particular etching is done of nitride etching will be removed here, and then this is here, this small, this is an oxide which is a very small, around 145 angstrom. Nitride is more 1188 angstrom. So we have removed the oxide, the nitride, and we have removed the oxide, and then finally this is the silicon. So we have removed the silicon by the etching. So there will be three different types of etching continuously, and there will be etch stop. You have to decide the etch stop here, because it's all there are two mechanisms of etch stop based on time, based on if the etching process is seeing a different layer. But here it's not seeing a different layer, it's silicon. I am going silicon. So here, because below also is a silicon, so I have to decide on the how the etching will stop at when a particular dimension has been achieved and a particular angle has been achieved. So this is the one unit step. The second step will be how to fill, because finally you have made this trench. You have to fill with a high density dielectric. You cannot fill it with a high uh, density dielectric, because then there is no compatibility between that material and this silicon. And what you have to do, you have to grow a thermally oxide. This white layer you are able to see, this white, this is a thermally grown oxide close to 100 to 200 angstrom. You have to grow thermally by a thermal oxidation, wet oxidation or a dry oxidation. You have to grow this because it has very good compatibility with silicon. This is silicon. This is thermally grown oxide. And now you can deposit your high dense dielectric oxide based on your chemical vapor deposition CVD, and CVD also low pressure LPCVD, plasma enhanced CVD. There are the atmospheric pressure ATM CVD. There are around 4 or 5 different CVD process, and the process engineer has to choose some process and define. So you can see this picture. So the first unit process will be etching. So it is doing etching only. You have made a wafer, all wafer, you have etched it and perfected that you are able to make that structure of etching of a particular dimensions. So this is the profile after etch. So you will only do this particular unit process only of etching, nothing else. Only thing is, all these, maybe you have etched, you have made thousands of trenches. So all thousands of trenches, you will measure their physical dimension. They have to come within a particular limit. So you have to perfect this process. Now here, what are the issues in this? I have made this unit process. This is the trench. I have made the trench here. This is the this is the trench, which is isolation, which is field area. This is active area. Active area, transistor will be there in this. You can see this is the transistor. So this is the transistor gate. This is the source. This slide you are seeing, this is the source. This is XJ, junction depth. And this is the source. And this I have put a tungsten, and tungsten plug is there and it's getting connected. Now, you see the aim is, as I told, to have a high packing density. Packing density means if there are two transistors, there will be a gate, source, drain, and there will be some isolation here. Next transistor, gate, source, drain. This is gate, source, drain, and some isolation. So this is poly to poly spacing. So I want to minimize, as you can see, half poly pitch. Poly to poly dimension is given in each node. In each process node, they give this. Okay, so if I want to reduce this dimension in this area, I can have more packing density. So one is this is I need isolation, it will eat up some space, right? Then this is a source. The blow up diagram is, this is a source. You will need some particular dimension of this area, this geometry. Which decides this? This decides by contact. This is the contact. You will have some contact size minimum. Say at 95 nanometer, contact size is 125 nanometer. It cannot be 90 nanometer. At 20 nanometer, contact cannot be 20 nanometer. It has to be 45 nanometer. Why? Because your contact resistance will increase, right? So there has to be minimum dimension of this. So if this is minimum dimension, there has to be some area here and some area here you have to keep, right? You cannot keep contact very close to the gate. So some spacing you have to give here. And now here it's an isolation where it's a trench. So in this area, there should not be any stresses because you are making a contact. If there are stresses developed in this area, it will affect the long-term reliability. Now the device may work, but stresses in this area will affect this contact, and this contact due to stresses may start breaking, and the life of the device may not be 20 year, maybe 5 year, 10 year, or like that. So all those things, all those considerations have to be given by the process people. That's why I say the process engineers, they are highly paid, and they have to know about the thermodynamics, about the mechanical parts, stresses, strains developed, chemistry, chemical, because all these processes are basically chemistry and chemical engineering, and there is a thermodynamics involved because you are raising the temperature. Some of these processes are at 1150 degree, 1200 degrees centigrade, and you are depositing one film over the other by way of a chemical process. So where the compatibility of two films have to be seen. So all those things are important, and the process engineer have to keep in mind. Now, what should be the minimum of this? If I make it say 118 nanometer, I will have problem in filling in CVD. In the CVD, because in a CVD, once you do, there is a conformal process. I want it a very good step coverage. CVD, it will come, wafers will come here, wafers will come here, and like that. And from here, you will get a void like this. This void, this area will not be filled. If it is aspect ratio is more like this, you will get like this, and that's all. So here will be a void. So this area will not be filled. If you keep it more, if you keep it 650 nanometer, there is no problem. So you will not get void, and CVD, it will be a conformal filling, but you are wasting that much area. So I have to decide between 650 and 118, which is the optimum this thing. And optimum they have decided, which is close to 300 nanometer. And 300 nanometer, once you have decided, then you have to make it dense lines and ISO lines. Okay, so this is the active area space. Many lines you have to print. Many lines you have to print. There is a difference between printing 2 lines, that is a ISO, and by printing thousands line. That's it. So you should be able to print thousands line with this particular this particular geometry, this particular pattern. You should be able to print thousands of time, one after the other, and it should look exactly the same. Okay, so this is how these things are made, and this is the example of a trench which has been very neatly made. As you can see, this is the trench, and this white is a liner oxide, which is a thermally grown oxide, and it is, as I told you, it is something between 100 to 200 angstrom in this dimension. It's a thermally grown oxide, and you can see this one white is a thermally grown oxide, and then you will put a dielectric, a high dense dielectric you will put on top of this, and then trench clean and all those things. So this is how the various specifications they will go, and this is the one. What I have done is I have made a trench. And as you recall, this is the active area AA, and in active area I have this is active area, and already I have a silicon here. What is this? This is silicon dioxide, 188 angstrom. What is this? Si3 N4, 1188 angstrom. Okay, so, and then I have filled it by a high density dielectric. The process of filling is PECVD. It's a plasma enhanced. Why plasma enhanced? Plasma enhanced process will take less time. If I do a CVD atmospheric pressure or a low pressure CVD, it will take more time, because whenever you design a process, you have to see the cost angle. Finally, you have to do manufacturing at a low price, at a low cost. Then only your this thing will be commercially viable. So you have to see all those things. So I have put this, and when you are putting by a CVD process, because you can imagine this thing is not deposited. So there is a trench here, and the material will go in the trench also. There is a hilltop. This is a hilltop. Some material will go here also, right? Some material will go here also, and so you have to ensure that material, that entire this hilltop and this trench, they are all filled with the proper your high dense dielectric material. And because our goal is to get a divert here at this end. That is why by filling we are ensuring that we are getting this kind of a structure here. Here where there's an STI, there is a overfill on top of STI. So this kind, and when you do this, after this, the process will be etching and CMP. And once you do the CMP, you will get a perfect shape. There will be some pictures where you will get a perfect shape after oxide CMP, and whatever your silicon nitride is there on top of this, you have stripped, and this is the active area. So this is oxide, which was 188 angstrom. It remains on top of here. Earlier it was silicon nitride also was there. So I have removed silicon nitride here, and here silicon dioxide is there. So here whatever silicon nitride was there, I have removed by etching, and that is how I am getting a divert like this kind of thing. This kind of divert I will get. So this, while in the flow there are around 7-8 processes, unit processes in this. So you have created a structure like this, which serve as a identification mark also for the next process. So this is one, and I will skip some of these processes because it takes a lot of time to discuss all these things. That is not the scope of this particular lecture. So only thing is, just I wanted to tell you that process is a complicated thing. It's very interesting, though complicated. So this is some of an example of a unit process recipe. What I mean by recipe, it's a active area H, which is the first process. So there is a anti-reflecting coating. So I have to do a backside anti-reflecting coating of 750 angstrom. How I have to do the coating? I have to use chlorine under argon and oxygen under plasma. It's a plasma etching, and plasma time will start and things like that. So all this information will be there in the unit process. At what temperature you are doing, what is the plasma time, what are the gases, what are the flow rates of various gases, that also will be given in a unit process. And this is the technology IP. This is the secret of the technology which no company shares. So this is what I mean about a unit process thing. Okay, so this I will leave all these process details, and okay, so about this yield is very important. Whenever any new process is developed, you will have two types of failures. One is random failures, systematic failures. There are two failures are classified at two types. So you will have random and you will have systematic failures. So you will have a yield, which is a systematic yield and a random yield. So when you start a new process, then what happens? The failures, systematic failures will be more, because there can be issues in the machine, there can be issues in your unit process, there can be issues in your design. So the systematic failures will be more, systematic yield will be less. So as you are seeing here in this path, this is the initial. You are getting some failures. So as you do on improvement, you have to study like failure analysis is a part of any process. If you are trying to develop something on the machine and you are not able to get the desired thing, then you have to find what is failing, what is that parameter you have to fix. So that is failure analysis. So once you do that, then only your yield will improve. So the systematic failures will keep on decreasing, and with time, and after some time, you will get only random failure. You will only get random failure. There will not be any systematic failure. So you can see here YS is the systematic yield is much more than YR random yield. But in the first part, systematic yield is very less than the random yield. Then there will be some random failures only. And how to do the yield improvement cycle? Basically, you have to you have to generate lot of data, how you will generate data. You have to make some test structures. There are guidelines what type of test structures have to be made. Then you have to fix the either there can be problem in the process fixation, the design fixation of those test structures, and matching of those. So you have to generate that data and identify the corrective actions. So yield takes a lot of to stabilize and to improve yield. It takes a lot of time, and these are the various equipments which you need for failure analysis. Imaging, FIB is there, focused ion beam, electron beam probing, thermal analysis, etc. Inline process monitoring. After each step, whatever process step you have done, there is an inline process measurement. Inline process measurement can be a film thickness, quality of the film, or electrical thickness also. So all these things are done, and to do, you see this below 20 nanometer with TCMC is able to do. That is very interesting slide I got from TSMC. They are doing 12-inch wafer. 12-inch wafer means 300 mm area. Now 300 mm area, if there is a particle which is of 20 nanometer size, then it can spoil their design. It can affect the yield. 20 nanometer particle setting, because you are doing the designs at below 10 nanometer node. So 20 nanometer particle is a big enough. It can spoil your yield. So you have to locate that after each step, because these particles may be formed during the process. Why they are formed during the process? There can be contamination in the equipment. Equipment can contribute, and or there can be, because it's a chemical process. In a chemical process, there are products and there are byproducts. Byproducts, the molecules, the gases have to be taken from the chamber. If they are not taken, they might get deposited. Some particle, some molecule may get deposited on the surface of the wafer, and that is a particle which will create problem for you. Okay, so if so after this step, you have to physically verify, visually see that whether this there is no particle sitting on the surface. Though you do three steps of cleaning are there, by using acid, using water, using alkaline cleaning. So all these three steps are there, but still some particle may be sticking. So you have to find that. So the challenge, if this particle is 20 nanometer, this finding these particle 20 nanometer in a surface area of 300 mm, you can say circular, is same as finding a coin between two cities on a highway which are 300 kilometer apart. You can see one coin. What will be the size of a coin? 2-inch at the most. So 2-inch and 300 kilometer will be the same as 20 nanometer and 300 mm. So this is the same geometry it comes. So this kind of perfection they are able to achieve. Another is the whenever you are doing a CMP, chemical mechanical polishing, you have to level the surface, and leveling has to be corrected to 10 angstrom after CMC. So 10 angstrom level correction, 10 angstrom level correction in 300 mm circle is same as leveling a 400-meter running track with flatness control, thickness of few papers. So you can imagine this kind of perfection is required for optimizing the yield and doing high volume production below 20 nanometer. And that is the reason only 2-3 companies, only Intel, Samsung and TSMC. And rather to a high perfection, only TSMC is able to do this. So this is how about the various process things. Lot of utilities are required. As I told you, there are bulk gases, nitrogen, oxygen, hydrogen, argon, helium. You need various gas plants. These are the actual pictures of our plants, and some capacities needed. There is a specifications on pureness of that material, which is of very high value. Ultra pure water is needed in a very high quantity. Resistivity of a pure water is 18.2 mega ohm centimeter, and you can see there should not be any particle in this, and the specification is PPB and PPT. So there are various mechanisms of doing this, and finally, what kind of contamination are there, and what are the methods to remove that contamination. So filtration, distillation, reverse osmosis, ultrafiltration, clarifying, adsorption, distillation. So here all these methods are there. Deionization, distillation, adsorption, degassing. So all these things are used to get a very pure water. So this is a ultra high pure water plant. It's a very complicated, very complex plant. And then there are 8-9 different types of tests on water itself. Ultra pure water, TOC analyzer, particle counter, silica analyzer. So these are the different tests. Your sodium analyzer, resistivity meter, TDS, this thing, total hardness titration. So all these things are done to ensure that the water, because water is used for ultra pure water is used at after every step. There is a cleaning. Cleaning is three. First is acid, then alkaline media, then ultra pure water, and then some high pressure air is put to dry that surface. So this is a standard cleaning procedure in a fab, and these have been standardized over the last 20-30 years. And the pure water should be only H2O. There should not be any particle sitting on it, because if there is some particle sitting on it, that will add as an impurity and it will add as a device on that. So then there is a nitrogen plant and all those things, pure things, bulk gases, nitrogen, oxygen, argon. It's required in high volume, and high level of purity is needed. These are the various, you can say, acids which are used, all sorts of acids, bases, which are used in the various steps of this thing. And then there are in the other utilities, you have power plants, 66 kilowatt, 100 and captive power, then your UPS, static, DG sets, and all those. Then PCW, process cooling water, compressed dry air, vacuum system, exhaust are there, and these are the actual pictures of our fab. And all, then you need manpower who are able to handle these poisonous gases. Then safety mechanisms are there. There are 3 levels of safety, because you are using phosphine, arsine, which is a highly hazardous material. So finally, I will skip some of these things related to reliability and all that. This is another, as I told you, when a batch is processed, how do you know whether you have processed the batch as per the limits? So there are test structures, and those test structures are put in the SLMs. That is why they are known as subscribed line monitors. And the various parameters of those test structures are measured. There are 200 different test structures we put, and they are measured in a wafer. Like this is the wafer. At each SLM, there are test structures, but we will measure at 9 different locations. across the wafer. At 5 or 9, you can decide. So like this, at different locations in the wafer, we will measure and we will see that those measurements are come within a particular limit. So these are the test structures like anvil, isolations, your different types of metal, your contacts, your low NMOS of a particular sizes. Okay, so this is a low voltage NMOS of a particular size. What will you measure? We will measure VT. Voltage should come like this. So this should be the voltage, the upper limit of the voltage and the lower limit. 0.320 and 520. It is some minimum, average, maximum, standard deviation, and all that. So you do this. So you can see these are the contact resistances. What should be the contact resistances? Gate oxide. Okay, the thickness of the gate oxide. How can it vary? Then your SRAM. Your SRAM, you will see the leakages and all that of 1 bit of SRAM. So all there are very comprehensive, close to 200 measurements are done, and then only the batch is certified to be as per the desired specifications. Then when the wafer comes, you have to test. This is automatic test equipment. This is the wafer prober. This is the head. On probe card will be put and wafer will be put, and this test head will sit on top of it to do a overhead sort, which is a overhead sort. And probers are different types. These are the different types of probe cards: rectangular ones, circular ones, epoxy. These are epoxy probe cards. You can see here you can have very low pitch, and these are needles, and this is the test head. This is the dot board, and there either socket is put as shown here, or this probe card is put. And packaging, you need a wire bonder, a die bonder. First die bonder, die is bonded, die is placed and bonded, then wire bonding to make the contact, then burn-in chambers and things like that. So these are the different types of equipments which are being used. So I will skip some of these things, and sure. So these are the different type of packages. So I will stop this, and you can ask remaining time. I have just 10-15 minutes more. You can please ask questions. In the meanwhile, I will try to answer.
Okay, thank you, sir. Please ask question if from the attendees, if you have any questions regarding the lecture.
Thank you, sir. Very nice information. Sir, I have one question.
Yes, sir. Yes, sir.
Yeah.
Please ask.
Yes, sir. How this process will change the this functionality? Suppose that 180 nanometer technology.
Yeah. Your question is how the process will change the functionality.
Your sound is not coming.
Basic reason.
Hello,
Please
can you please
repeat the question. Repeat the
Yes.
question, please.
Actually, 180 nanometers technology, TSMC is also providing, and SCL Chandigarh is also providing, but their functionality and reliability is different. What is the basic reason, sir?
Yeah, because the basic reason is the design of the transistor is different, right?
Okay.
Let me, because the design, that is the process. Engineers will define they will design the transistors, and what is difference in the transistor, like very minute differences. It's not a very huge differences. I will tell you. You see the transistor, whatever transistor we have studied, like we have an oxide, gate oxide, and then we have a poly here, and then we have a source drain like this, and then we have a here isolation. Okay, so now
Yes.
what are the issues? This is the substrate, choice of substrate. Now what is your thickness? They will give this parameter. They will give gate oxide thickness, the TOX. They will give this. You can check their gate oxide thickness. That will be more or less same. Then
Yes,
this is
almost same.
no, almost same. Then this is the exit. This is the junction depth. They will not give these kind of things. Then what is the junction depth? What is this geometry? They will not tell. And like in a gate oxide, whether it's a purely silicon dioxide, normally our thing is not it's not a silicon dioxide. It's a nitrated oxide. There is some nitrogen, 5%, 10% nitrogen in this to make this better transistor, to improve because here the channel is found below this interface, and adding nitrogen here affects the mobility here. So your ID sat is better. Our ID sat is 600 microampere per micrometer. You can check there. So what is their VT? Our VT is 420 millivolt. Their VT will also be within the same, maybe 15-20 millivolt here and there. Reliability is, you see, it depends on your design of this product. But SCL is a tower judge, and tower judge 180 process is very good. There is not much difference. And I will tell you, these processes were originally made at only one or two places. 180, 350, they were made at IBM, and later on people took from there and incorporated some changes. Like they incorporated how to do these contacts. Earlier contact was of aluminum. Now they are doing with the tungsten. So these small changes in the geometry, small changes in the process with respect to the which chemical you are using. So that affects to some extent the functionality of the device. That is the only reason.
Otherwise, I have seen that threshold voltage is almost same for both the technology.
Almost same. Almost you will see the difference is 96-97% is same. 2-3% difference only. If you have realized a circuit in a tower judge, simulated it using tower judge P-Spice, H-Spice or whatever tool you have, simulator you have, using tower judge models, then you simulate the circuit using TSMC or Global Foundry. Use the same circuit. You will see very less difference. Some noise may be better, or I don't know. I have not compared, but you can see the noise part. You can see the bandwidth part. They will be more or less same. Little bit of changes you will have to do. Majority.
And sir, there is any source for this SPICE file for SCL 180 nanometer?
Yeah, you can ask. You in the PDK it will be there. If it is not there, you can ask them. They will give.
Okay. Like
It will be
TSMC is providing this for
notebook.
academic use.
Yeah. You can take. I think it's there in the source in the PDK. Na elaborate is there. You can open in a notepad. Spice file. You can see various parameters. There are around 80-90 different parameters. Their name is there. The value is written. So those values are there. It's given there. That file will open in a notepad.
And sir, SCL is still relying on only 180 nanometer technology, or there is any plan to shift for lower technology node also? Like
no. Right now there is no plan. Only 180, because the thing is, we have to do, first of all, demonstrate high volume manufacturing at 180. There's a huge market. Even our space and defense requirement 60% is at 180, 350. And even now, if you have a Google, you can use Austrian Microsystems, AMS.
Okay. Yes,
no,
sir.
I worked for 2 years there. Austria Microsystem. It is there in Austria. That fab, it has 3 lines, 180 and 350 only. Doing business, $2.6 billion. $2.6 billion business they are doing. Industrial, automotive chips. They are all for all Europe. Industrial chip, automotive chips, they are doing that. So,
but sir, for digital nodes, sir, for digital design, it is not suitable.
Digital design, it is not suitable for processor. Processor, anyway, we cannot design and make. It's a processor and memory. If you need a 8-bit, 16-bit processor, you can do very well do in 350, 180 also. The processor which are used in car, they are based on 350 node. You don't need a low, and all the material, all the components used in space and your defense, they are not at lower node. The reason is very simple. You see, at 1.8 volt device, noise margins will be more as compared to the device which works at 0.8 volt.
Correct, sir.
Lower transistor below 45 nanometer transistor, pure digital, they work at 800 millivolt. So noise margins are very, very small.
Very small.
And which is not feasible. You need very, very high reliable or rugged devices for space and military applications. For industrial, lot of things like you have your AC, fridge, and so many things, gadgets. There you don't need these 45, 32 nanometer. Okay, so each market is niche area. So lot of devices in these things, and only thing is we should be able to demonstrate. You see, designing is one part. It is not, you have to make a device at a price at which it is sellable in the market. ADCs you will get for 200, 250, 300 rupees. But can you produce a device for 250, 300 rupees? That is the challenge.
Yes.
Right. So it's a, because if you are running a commercial thing, you have to meet those. Now, price is not in your hand. Price the market tells you, and there is a competitor. You are not starting the first time. Either you come out with a product which nobody is having. You can ask whatever price you have. So that is not the case. We are starting and we are making some product which others are making, and others are making for the last 30 years, 40 years. We cannot make better than them. This is very clear. They have a lot of data, liability data. We don't have anything. And moreover, their plant is whatever investment they have done, capex. So all that is free now. So they can afford to reduce this. So in a business kind of scenario, there are a lot of other things matter. So whatever R&D cost is there in a product, the company realizes that whatever R&D cost when it comes with a new product in the first 1 year. After that, they drastically reduce the price. You can see the whatever component it is. Initially, the prices are more, and finally they will reduce. And the same is true for your garments like Arrow shirts. When the new shirts come, it is priced at some level. And once their 50% of the quantity of that is sold, they have made enough money, and then they will give you 30%, 40% discount on the remaining thing. So the same thing is here also. So here, whenever either you have some idea of some new chip which is not there in the market, so you can ask for any money. If people need it, they will buy it. And once a second or third person comes, you reduce your price, and it will be difficult for him to meet because he has to. There is some R&D expenditure involved, design expenditure involved. So all these things are marketing strategies and things like that. So one is to, it's a learning process. Design is one part. Another part is running a commercially successful unit. That also is a lot of things are involved in that also, in pricing and things like that, right?
And sir, one more thing I want to know from you, that because you are in the fab industry. And what about, sir, Google Skywater 130, sir?
Good, very good. Use anything. All these process don't, all Global Foundry, QMC is there, Euro practice is there. There are 3, 4 are there. Tower charge is free for you. Mighty will fund that. So all these are good. Use anything. Learn the design part. Learn concepts in the design. Use any foundry. No issue.
And how much? And what is this step out time, sir? Suppose that it is submitted. So how much time
6 months.
generally? Because
6
for
months,
ACL?
6
6
months.
months.
6 months, minimum 6 months.
Minimum. Okay, sir. Thank you, sir. Thank you so much, sir.
Thank you, sir. Thank you.
Okay, next question, please. If anyone wants to ask.
Okay, so we can wind up if no questions are there. Thank you very much for this.
Thank you, sir, for being with us and for your thoughtful knowledge in sharing your thoughtful knowledge in the process development field. So we are really thankful for that.
Thank you, sir. Thank you. Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you.
Thank you, sir.
Okay, next class will be tomorrow morning from 9 a.m. So, which will be taken by Kang sir. So please be at time, because the time where he is staying is at that time will be around 8:30 p.m. So please be on time tomorrow at 9 a.m. Thank you. Thank you. This is the end of this session and end for the today also.